All right, can you folks see
Excellent.
my?
Very good.
All right, good. Good morning. Thank you all for coming, and thank you, National Science Foundation, Department of Homeland Security, and all the agencies that support our research. My name is Zhong. I'm professor with Computer Science Department at Yale University, and I'm the Computer Systems Thrust lead for the Athena Institute. And it's my pleasure to give you an overview of our envision activity for AI-powered computer system at the edge. So our thrust consists of scholars from Duke, Wisconsin-Madison, and Yale University. You can see some of us, our names show up in multiple threads because although we kind of present the research in thrust, but truly our proposed research activity is cross-cutting and have a lot of synergistic efforts there. For the computer systems thrust, our ultimate goals is efficiency, programmability, availability. The future of mobile network is computing, and this computing will be carried out by software running in distributed shared infrastructure. Give me 1 second. In this thrust, we'll study the computer system in these infrastructures and develop AI-based technology to make them efficient, for a greener planet, programmable for fast innovation and continuous evolution, and available for supporting mission-critical services. We will produce designs, implementations, and evaluations of algorithm, software system, hardware, all openly available. The core team of this thrust include members from Duke, Wisconsin, Yale, with collaboration with others. Edge data centers will shoulder much of the computational needs by future mobile networks and services. Suma has already kind of give you a preview of this. I would like to give you one specific example from my own research, right? Massive MIMO, a key 5G technology as an example. 10 years ago, my group reported the world's first massive MIMO prototype using an array of expensive FPGAs. Last year, we showed for the first time that massive MIMO physical layer actually can be realized in pure software running in an edge data center. However, this is not enough. We must improve the data center efficiency and availability to match those of the specialized dedicated hardware used in base stations today. We must satisfy the diverse performance requirements of mobile networks and services on top of such a shared infrastructure. We will leverage 3 related opportunities to look into how to design and optimize the future edge data centers. First, we will disintegrate data center resources, such as CPU, memory, and actuators, using programmable network switches and fast Ethernet emerging on the horizon. Second, we will apply AI technology to manage the diverse and network integrated resources. And finally, we will design hardware actuators for both AI and network functions, leveraging the insight that both machine learning and wireless physical layer extensively leverage tensor operations with fixed point arithmetics. Later, my colleague Anurag Khandelwal will present his vision about the interaction between AI and disaggregated data center designs. Edge devices such as smartphones, autonomous systems, and IoT devices connect a mobile network with the physical world. They have diverse hardware, diverse trust models, and diverse performance requirements, to which we believe AI holds promise of solution. In the systems thrust, we will investigate operating system and programming support for deploying AI-based services to them. Wenjun, who talked about his metasurface work before, but he actually has done excellent work showing very promising results to support distributed learning from a large number of diverse embedded devices. Because of the nature of interfacing with the physical world, security, privacy can also be very important, and we must tackle the edge. My colleague Mike Rader at Duke actually have pioneered the work, the solution called behavioral verification to detect IoT devices that have been compromised at the edge. Later, my colleague Yang-Han Kim from Wisconsin-Madison will talk about his work about energy optimization of AI in edge devices, especially in the context of agricultural applications. Mobile networks are emerging as a computational system with resources distributed nationally and even globally, owned and operated by different parties. Yet together, they must provide high availability to support mission-critical services. Our control plane research targets at optimizing the management and operation of this distributed heterogeneous system, which has a huge configuration space, thanks to hundreds and thousands of tunable parameters. In particular, for example, the newer generation of mobile network simply have a larger configuration space with orders, magnitudes, and more tunable parameters. We will not only utilize AI technology to search for performant configurations, but also explain the performance of a given configuration. For this, Wahid and Helen from Duke have shown a promising direction with causal analysis. It is worth noting that explainability is one of the roadblocks for the wireless industry to adopt AI-based optimization. We cannot just hand them a solution that works. We must explain to them why it works to inspire confidence. We will also employ AI technology to substantially improve the infrastructure availability. Krish from Duke has shown it is possible to predict failures of network routers using machine learning. Such prediction can be coupled with preemptive fault recovery to contain the impact of failures. As I mentioned, Mike Rader from Duke has shown it's possible to detect compromised members of a system by comparing the behaviors with their peers. Again, a very fertile ground to apply AI, especially machine learning. That's what all I have. I'd like to give the podium to Anurag to talk about his vision about AI and data center disaggregation.